Okay, so today is all about you guys trying to get everything squared away and get you comfortable with the material. So open the floor for questions. I also have all the homeworks loaded up on PowerPoint. So yeah.
Can we do number 6 on? I think it's that. Yeah, that homework.
Number 6 on number 6.
Yeah.
Okay, so this is So the the aspirin has a pKa of 3.5. The pH of the stomach is approximately 1. While the pH of the intestines is approximately 6. So calculate the fraction of aspirin that's ionized in the intestines. And so we're looking then at a pH of 6, and we're comparing that to a pH of 3.5. So this, again, you will have this equation on your little equation chart. I think it's this set of notes here, that percent ionization equation. You could do the ice table, or you could cut right to this point right here. Yeah, so let me move that out of the way. And so this would be the equation. So let's try to figure out, this is for an acid, and we have that on this one. See, it's percent ionization for an acid. And so that would be the pKa of the acid, meaning the acid is neutral and it produces an anion, which is ionized. And so this is the percent of products, if you will. Okay. And so if we look at the homework, we see that this is aspirin is acetylsalicylic acid. So that's great. We're going to use this equation, and we don't have to subtract from 1. Okay, so we'll do it for a base too, just to show. So let me go ahead and take this problem here, and I'll paste it. Let's see. Let's do this right here. I'm going to create a blank slide here. Okay, and just grab this equation. Okay, and I'm going to grab this problem here. Look at those skills on PowerPoint. All right, so there's our problem. And if I make this go full screen, then I can do the work. Okay, so now I can use my little tablet. So percent ionized for an acid is equal to this 1 over 1 plus 10 to the pKa, which is 3.5, minus the pH, which is 6. Okay, so that's 2.10 to the minus 2.5. So 1 over 1 plus 10 to the minus 2.5. Is that correct? Okay. And so if you're looking at that, I'm adding 0.00 something to 1 in the denominator, and so this is roughly equal to 1, which would be 100%. So it's very close to 100% ionized in the intestines. We also know that because so if you've got the acid HA plus water is in equilibrium with the base H3O plus, and this is the conjugate base A minus, and this sort of occurs at 3.5. So at 3.5, you're halfway there. So if we're at 6, we're far on the right. If we're at 2, we're far on the left. So you can kind of think of it that way too. So let's do this for a base though. So let's say this was, let's scratch this out and say, so for, I don't know, scary drugamy. HCl. All right, so that's just sort of 2 signals. It's an amine that signals that the name is telling you it's a base, and then you see that HCl. That means to crash it out of organic solvent. You bubbled in HCl and you protonated the base, which made it a cation, and then the chloride made it an anion. Now you have a salt, and it forms crystals in the organic solvent. It doesn't want to be in the organic phase because it's ionized, and so you get these crystals. And it has a pH, has a pKa of 3.5. Okay. Goodness gracious. Slow down. Okay, so then that how do we write that out? Well, we would have then this BH plus H2O is H3O plus B, okay? And that's 3.5, right? It's the same pKa, and the pKa goes with the acid form, the BH plus piece. And we're at pH of 6, so we're far on the right, which means it's not ionized, okay? So it'd be 1 minus 1. It'd be 0% ionized. So all of the reactants are gone. And so this would be roughly 0% ionized. So it's 1 minus the percent ionized for the acid equals the percent ionized for the base. Okay, maybe I should do 100%. Since we're dealing with hundreds, you know. But anyway, what you've got then is, since the ionized species is on the other side, we've got to look at, we kind of invert it, yeah. And so it would be essentially 0% ionized. So this scary drugamine would be 0% ionized, whereas the acid would be 100% ionized in the intestine. Okay. Did that confuse anybody, or does that help? Okay. Okay. Now I got some emails from folks with questions. You can help, you can ask your questions now. Yeah. Yes.
So we could do the same thing for homework 10, number 1.
Let me look. Okay, let's keep those for now. Homework 10, number 1. Let's see. That's number 8. Okay, let's go on. Yeah, so you do the same. Compound C above has a pKa. So what I'm asking you, here's compound C, and you're looking at that, and it has a pKa of 9. But what I'm looking for you to be able to do is, you have a tiny piece of information missing. You have to look at the molecule and recognize that it's a base. So it's the same kind of calculation, yeah. And then the stomach, we know, has a acidic pH, and so you really don't need to do once you're more than a pH unit away from the pKa, it's either 100% or 0%. You know, so it's only when you're, you know, a half or 0.7 pH units, you know, close to that pKa value, that you really even need that equation. So if I've got a pKa of 9, remember what this pKa of 9 is telling us. Let me go ahead and let me do this. I'm going to grab this guy and y'all use the snipping tool. Yeah, it's so beautiful. Yeah. Okay, so I'm going to paste it in here, but I'm going to create a new one. Oh. There we go. Okay, so the reason I'm doing all of that is, again, just to show that if we call this, whoa, gotta make it go. If we call this whole molecule B, then the pKa is for BH plus. Okay, and so we have, again, BH plus water is in equilibrium with H3O plus B, which is neutral, and that 50-50 point is at pH of 9. And the stomach has a pH of 1, we say. So at a pH of 1, we're way over here on this side, BH plus. You could also think of it in terms of that partition diagram, where you have pH, and at 9, you have this line here, and for this molecule, you have B on this side and BH plus on that side. If you wanted to know like what it was at 9.3 pH, then you would need to use that equation, or 8.7 or something. Then that equation will tell you specifically what the percent ionization is. Does that help? Yeah. Okay. And then you just look to see which one's the ion, and the BH plus is the ion. So in the stomach, it's 100% ionized.
Can we go over like kind of how to identify whether things are acid or base? Because I sometimes get confused when I see nitrogens and like a bunch of oxygens.
Yeah, sure. So let's go back to that screen here. So just any of these nitrogens are going to be basic. So these right here.
So even if there's like OHs in the molecule also?
Yeah, like this one, this would be a basic nitrogen, and this one would be a very, 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 three varies weak acid. Yeah. So the pKa of 10 is really talking about this one here, because the amide nitrogens, some say they're not even bases. Okay. And in this case, when we're talking about pH of 10, we're talking about the OH. So let's say this. So this group right here, I'm going to draw it over to the side. R1, N, H, C, double bond O, R2. Okay, this hydrogen, I mean these lone pairs are spread across like this whole region of the molecule. And so because they're so delocalized, they're communicating with that carbonyl, they really aren't pH active. They're not really going to steal a proton from water. And so I just saw the nitrogen and said, oh, this is basic. But no, that's in an amide. And so you can just ignore amides in terms of their basic. So ignore amide nitrogens, or amide nitrogens. When identifying I'll say bases because that's what we're talking about. So in this molecule, when you see the pKa of 10, you're like, whoa, that's it seems like we have a base. Well, it is. If you pull this hydrogen off, you have a pretty strong base. Like if you have sodium in place of that hydrogen and you put that in water, it's going to steal a proton right away, and it's going to be a very strong base. It's a very, very weak acid. So that's like a seesaw. If you got a strong base, it's a really weak acid, and vice versa. Okay, so then over here, there's no nitrogens in this molecule, and you've got the acid, the carboxylic acid group. So that's pretty straightforward as an acid. Here's a tertiary amine. It's not an amide, so you've got those lone pairs that are the basic pairs. Here's a tertiary amine. It's also going to be, pH active. And then this is very similar to an amide, okay? And so we would ignore that one. This is the one that we're talking about with the pK of 8. Okay.
So, from compound E, would that one
so this would be, this is the neutral form right here. But this guy right here is not, I've never seen a pKa given for that OH. Really, the phenols, just a single ring, that group right there is the one that has the pKa of 10. But like this, we got all these other fused rings. I've never seen a pKa for that OH group. So we're talking about pH of 8 being this guy right here. Yeah. So that's a base. So then you would write this out, if it's pH is less than 8, then again it's going to be BH plus, right? And greater than 8, like 9 and above, it's going to just be this neutral molecule.
So going off of that, for the second question on this homework,
Mm-hmm.
that molecule would be for the CH plus.
Yeah, let me find it. Let's see. So we're going over here. The second one is compound C has a pK of 9. Call it C. What is the species most abundant in the stomach? Okay. So yeah, you could do that pH scale, draw a vertical line at 9, and then if we look at C is a base. And so less than 9 would be BH plus or CH plus in this case, and greater than 9 would just be C. So it'd be CH plus.
Yeah, I just didn't know how to differentiate between the CH plus and the CH2 2 plus. That was
Okay. Yeah, the CH2 2 plus, you would have to have 2 pKa's. Yeah. So in that case, over here on the PowerPoint, let's go back to this one. We don't have a dibasic molecule in this set of molecules, but if it were dibasic, sometimes you see, like might have been in the earlier homework, it said a dibasic molecule. Yeah, so dibasic pKa equals, say, 4.5 and 7.6. Okay, then you would draw your little speciation diagram like this, and at 4.5 you'd have a line, and at 7.6 you'd have a line. And so this is a dibasic, okay? So way over here in base, you've pulled all the protons off the molecule, and so it's just B. And then in this case, you're past one of the pKa's, and so then it's BH plus. It's been protonated once. And then all the way in the stomach, where it's very acidic, you've protonated both bases, and so you have BH2 2 plus. So there's protons on 2 of those amines wherever they are in the molecule. And it's really helpful for you guys to get comfortable just using these generic terms for your molecules, because they're ridiculously big. You know, you're not going to write out all of this. You're not going to use the name, or you're not going to be able to draw the formula. It's not going to make any sense. And so you really have to generalize things and use like A for acid and anion, and B for base, and then put a proton on it, because that's what you're doing, and making it positive. So this will be very useful later on when you're trying to talk about pH and speciation to somebody. If you're comfortable saying, well, this is a base, so I'm just going to call it B, and when we protonate it, it's BH plus. Yeah. So I'm just trying to get you comfortable with that.
On the exam, if we're given like a compound, are we going to be given?
This will be the way the exam is. This kind of panel with lots of questions about the molecules. So you'll see this. It'll just be different molecules. It's always hard for me each year to try to change it up. It's like, okay, what molecules can I put in there? You know. Yeah. Y'all heard of this new trank that's being mixed in with fentanyl? Have you heard that in the news? Yeah, it's happened like this past week. It's really hit the news. I'm going to try to find that Zycal or whatever that molecule is, and see if it's a base or an acid. So keep everything relevant, you know. But anyway, yeah, so the scary thing about that is it doesn't respond to Narcan. So it's hitting a different receptor, so the Narcan's not stopping it. So they have this mixed in with the fentanyl. It knocks them out. The Narcan can reduce the fentanyl exposure, but this other stuff is still sedating them, and they can't breathe. And so they said that people are dropping like flies over that stuff. What is it? It's a tranquilizer that they're stealing from veterinary, streams of supply streams, and they're mixing it in with fentanyl to see how much they can mix in. It's cheaper and produces a lot more of an effect. And it's for large animals, so it's kind of like that carfentanil that I was talking about. They're really small doses will knock you down, and so they're mixing in too much right now. So they're kind of using. I heard the news report on this, that they're using us as sort of our, like if they're killing too many people, then they back off on the new ingredients, and then so they're adjusting the stream by because if you kill off your buyers, they're not going to buy again, right? So they're trying to adjust it and stretch supply and so on. So they're basically using us as lab rats to figure out what the right mix is. That's pretty crazy. Yeah. That's not on the test though. So let's keep going back to, I don't want to get distracted and tell stories all the time. Yes. I'm sorry.
Homework number 8, can you go for number 4 and 5?
Number 8, 4, and 5. Okay. So the alkaloids. Yeah. Okay. Yeah. This one is kind of a. Let's see. Yeah. This is just the unit conversion, trying to work your way through to the number of pills. Okay. And so let me grab these guys. Snipping tool. Okay, and that's going to be in drugs and pharmacology. Is that the right one? Yeah, here we are. So let's go down here to the first order kinetics one. Yeah. So put it right here. Yeah, it worked. I'm surprised. Okay, so we have this lethal dose, and what we want to know is how many pills we need. Okay, so one pill is 325 milligrams, and so that's going to be a conversion factor. And so this problem is really just trying to show you how everything really can be a conversion factor. Okay, and so we could start with this. Notice how, and this is the way I do these kinds of problems. We're asked for a single number of pills. So let me say we're asked for a number with a single unit, right? Think about a concentration. A concentration is a double unit, right? It's like milligrams per kilogram or moles per liter. That's a double unit. So this is a technique I use for stoichiometric calculations. If I'm asked for a single number, I probably want to start with a single unit number. So I've got all these numbers here, and yet this one's got a single unit, pounds. And so that's what I'm going to start with. I'm going to say, okay, 130 pound female, okay? And then I'm going to convert that to kilograms, okay, because I've got this dose here. And so I've got, let's see, 1 pound is 454 grams, so that's 0.454, and that's on the periodic table that we have, kilograms. So in your test packet, you'll have that conversion on the periodic table. So that's kilograms, and then I've got this that converts it over to the LD50 dose. Let's see. Okay, lethal dose. So when we're talking about lethal dose, that's really what we're meaning is the LD50. That may have been a question that you had. Is that the same thing? And it is. So we have 225 milligrams of aspirin per kilogram of body mass. Okay, so you see how all the units are canceling, and then we have the conversion over to the pills. So 325 milligram aspirin, goodness, per pill. So it all works out nicely. Let's say I started this and I ended up with pill on bottom. I can still do all the math and just divide by 1 at the end, or 1 divided by that number, invert it. But it all worked out. I've got pills on top, and so we're going to end up with a fractional number of pills. This is the one case where you would round up, okay? Because we're not going to say that they were trying to, take a bottle of aspirin and they calculated, I'm going to take 1/3 of a pill there at the end, and that's going to really do it all. This would be, the number of pills that get you just above the LD50 would be a 50-50 chance of dying, maybe a little bit more since you went above the LD50, right? So it's when a pharmacist commits suicide, right? They do the math and they're like, okay, I went 0.46 pills. So this should be 40 point something, and we get 41. Did that clear things up? Okay. Now let's see. Much aspirin remains in a 130-pound woman after she took 2 of these tablets. The plasma half-life for aspirin is 17 minutes. And so we got to figure out, let's see. We're really just assuming that this goes into the body and that goes into her plasma, and then we just have to do first order kinetics on that. So we really just have 2 of these. So 2 times 325 is 650. So that's how much aspirin is in her body. Okay. And then we're going to use this first order kinetics equation, which is on the previous slide here. So here's the equation, and it's going to be that times this amount. So the amount at some time later is equal to the initial amount times e to the minus t times natural log of 2 over t 1/2. So that's 650 milligrams of aspirin times e to the minus, and it says after an hour. Okay, so we've got 60 minutes here. And 17 minutes here. So let's see. Just make sure I did the work right. Don't forget to change the sign, and then do the e to the x, and then 650. 56.229. Yeah. Places where people go wrong is they miss this negative right there. Okay. Can you, like, were you tripped up by having the mass and not knowing what to do with it? Yeah. Okay, so yeah, again, so this was the clue right here, is you're given a half-life. And so when you're given a half-life, you're like, oh, wait, that's kinetics, and we only learned a first-order kinetics. And so on your equation sheet would be this equation right here. And so this would be an example where if you didn't catch the clue right here, okay, then you wouldn't know what to do. But if you caught that clue, you're like, okay, that's first order kinetics. I've got an initial amount here, and I've got the half-life here, and I've got time, an hour. I've got time here. So I've got all the pieces, and I can use that equation to figure out the concentration sometime later.
And you said this is on the equation too?
Yes. And so is the other version of this. So if we want to solve, say, for the half-life. So I say a patient has this new drug in their body, and we measure their concentration, and then an hour later we measure the concentration, and it's dropped by this amount. What's the biological half-life? So that could be something that we could do. And so, in that case, let's move A0 over to the other side. So we have AT over A0 is equal to the e to the minus, I'll just do t over t 1/2 times the log of 2. Okay, so then how do we get rid of the e? Take the natural log of both sides. So then we have ln AT over A0 is equal to minus t over t 1/2 times ln 2. And so you'll have this version as well, which you could solve, like you could move the t 1/2 over here, move the natural log over there, and I would solve for t, or vice versa. But just, you'll have a couple of versions of this equation that may be easier for you to do if you need to do any algebra. But first order kinetics, you've seen it probably second semester freshman when you cover kinetics. I'm sure you've seen it in biochem. You see it again here. So the third time you've seen it, I really hope you're comfortable with first order kinetics. It's just ubiquitous. We see it everywhere. And so that's why it's on this test. I want to make sure that you're comfortable with it. Yeah. if you haven't understood it in the past, now's your chance. It's that growth mindset. Say, I can't do that. Say, you put yet on the end, right? You'll figure it out by Thursday. You have a question?
So I was rewatching an old lecture from last year for the colorimetric lecture, and you had said to, like, you were talking about the drug flashcards, and you said to memorize something about color, and it really threw me off. So, like, can you just clarify what exactly?
Okay, I may have said. Let me find it.
Like, because you were talking about the dyes, like.
Yeah, so I think you should. Yeah, I want you to memorize the 4 chromophores of the dyes, not the drugs. It's not really related to the drugs. It's just the chromophores for the dyes.
And
so let me find that. Here's the drug flashcards. I don't have the colorimetric compounds on here, okay? But they are in the lecture notes. So here are the 4 families of dyes. And so you're looking for this carbon here. That's that methine. It's a sort of a carbon with 3 bonds. They've shown this double bond here, but you can move those electrons around and get rid of that plus. This guy can move this plus over here, and I should be able to get it onto that carbon. It looks like it's not going to make it, but you should have a carbon with 3 bonds. It's going to be positively charged. That's that triarylmethine. And then we have the carbonyl dyes. So it's an extended pi cloud. You see this extended pi cloud with those non-bonded electrons on the carbonyl. So that's a chromophore. And then the nitro groups. And so typically, I guess in the explosives, most of those explosives are yellow. Some of them are orange, and it's because of those nitros. So they're nitro dyes. And then here's an azo dye. So this azo linkage is this right here. So those are the 4 pieces that I want you to memorize. If you get these molecules or molecules like them, and I say, what type of colorimetric or chromophore family is this dye or pigment related to, you would say, oh, I see the azo group, so that's an azo dye. So you would select that on the multiple choice. Okay. So you comfortable with that? No, but I can't tell you which one of these is what color they are.
Right.
No way.
That's what I was like.
No, they think of that. I mean, yeah, that would be great, but I'd have to go to Gaussian and whew, yeah. We do that in graduate school in the graduate spectroscopy course. I have them pick a dye and they model it in Gaussian, and they model the RGB lab, and they predict the color of that molecule using Gaussian and then compare it to the real thing. And some of them hit beautifully and others are way off. Yeah, so it's different. I haven't analyzed why some dyes work with Gaussian and others don't. But some of them were great. This chrysanthemum dye that one of the students did was so beautiful. It was like it was a red, but red doesn't quite give it the effect, right? Like with D, it was red.
I did have one other question. I think it was the last homework, homework 9. It was asking a question about first synthesis and like salting out was.
Okay, salting out was probably the point, yeah.
But I was like, do we need to know what the synthesis part?
No, but you should know if it's an amine, like a basic amine, then you could salt it out from an organic solution. So that's just a term that goes with bases. So if you have a base, like we could go to these. Let me try to find the question you're asking about, though.
Because in the notes it was like the first synthesis of meth, and so I was
yeah. But it's that last step in that synthesis. But then I had a sort of a general set of slides on it about salting out. I had all of the little hydrogen HCl generators, little ketchup bottle and the gas tank. And do you know which one it is that you're talking about?
I know it's on homework 9. I just don't know which.
Oh, I'm looking at homework 10. That's why I'm not finding it.
Yeah. I don't remember which.
Way to go. Anyway, but that's the point that I was trying to make was, so let's go to the drug flashcards. Okay, so on this page, again, that's an amide, so we're not interested in, none of these would salt out, okay, of organic solution. Yeah. And then these, anywhere I see those basic amines, so this one, cocaine, it's a metabolite of cocaine, so this benzoylecgonine, that's the best I can do, would have that HCl, and that would form the salt, and it would come out of organic solution, like if you have it in the ether layer. Here's morphine. Again, you could salt that out. This guy, this is like an amide on steroids, right? Because it's a ring-based amide. So, yeah, I don't think this would salt out. Yeah. So, again, you see that carbonyl next to an NH. So, no.
So it doesn't apply.
Yeah, it doesn't apply to the amides. Yeah, yeah. And so then here's that tropane ring. Any of the cocaine or cocaine derivatives would salt out because you have that. Yeah. Procaine. Yeah, you've got one here. Yeah, I'll just draw the lone pairs, and here, and then quinine. Yeah, I mean probably. But this would be the one that would be the most. That's a terrible lone pair. It's just okay. There, better. These again, it's this one over here that's going to be pH active. So either that one or this one, they kind of alternate. So yeah, this one would salt out, but these guys would not because they're amide type linkages. It's just a circular one. And the reason that's the case, that they don't really behave in a pH active manner, is those lone pairs are delocalized. And so you really, if we've got water and it's got this proton on it, it's not going to be attracted to a delocalized set of electrons. It's going to be a localized lone pair, like on an oxygen or a nitrogen. That's why oxygen and nitrogen are the ones that really are pH active. Like you wouldn't think that an aromatic ring, I mean, there's a lot of electrons there. Why aren't they basic and accept protons? Because the electron cloud is distributed over the whole ring, so it's not going to steal a proton from the water. Water wants it back. Okay. And LSD, you've got we got 3 on there. 1, 2, and 3. So organic chemists are so lazy they don't put those lone pairs on anything. So, but they're better at drawing than I am, so I got to give them that. Lots of amines here. Doesn't look like the cannabinoids are very, they're not basic. This is, I don't know how pH active they are actually. I mean, again, these are hydroxides or hydroxyl groups put on fused rings, and morphine, the OH on morphine is a hydroxy group on a fused ring. See up here. So these guys, we don't have pKa's for those guys, so we probably don't have them on the cannabinoids. So but this one is an acid, so that's pH active. And a lot of the metabolites, they'll like put an acid group on it to make it more water soluble so that you can pee it out. So the body's trying to get rid of these things, just metabolizes them. If it can get energy from it, then it's like food. But if it's just a contaminant in the body, and it goes through the liver, the enzymes will put oxygens on things, or put hydroxyl groups on things, or make acids out of them, and then they're water soluble, and then they just leave the body through the kidneys. A lot of the stuff that's not water soluble just stays in the gut, and you poop it out. So it's this really like small molecules that are soluble enough to get out of the gut and into the bloodstream. Then they do crazy things in your body, and then the liver metabolizes them and gets them out of the body. So, That's the extent of my knowledge on toxicology. But it's a broad brush, and I think I'm on safe ground. I'm not going to tell you something that I'm fuzzy on. Next question. Yeah.
There's a question on homework 10 that's kind of similar to the absorption of the drugs that we were talking about earlier. I just don't know where in the conversions you would get to weird.
Oh, it probably uses that volume of distribution equation. Yeah, from the toxicology lecture, there's a volume distribution. Where are we? Okay, back up here. There we go. Yeah. So that's, let me go ahead and snip that one. Okay. And then that's the drugs and pharmacology lecture. And let's go back a little ways. It's this equation here. So I will create a new slide. And so this, I think, is a plug and play calculation. So what do we have? We have, let's go back and look at the equation. We have the apparent volume of distribution here. We have the dose in milligrams. K is the body mass in kilograms, and then the plasma concentration in milligrams per liter. So 200-pound man, we're going to convert that to kilograms. We have the dose in milligrams, so 400. That's D. This is K. And then we have the apparent volume of distribution, which is about half a liter per kilogram. And so he's going to have so many kilograms in his body, and half of those kilograms are essentially, water. And so then we have all three, and we just solve for CP. Yeah. So quiet. Did you have your question?
I think it's more like 7 questions here.
Okay, sure. 7, question 3. Yeah. Okay, so then we have this split. Let me grab this and put it in. Okay. And that's going to be in pH partitioning. Okay, so this one up here, I have, this is a good one. I'm going to go ahead and do 2 as well. Okay, so we have quinine. And heroin. Okay. I'm going to call it HN. I always have a hard time. What do you want me to call heroin? I don't want to use H because H is a proton, right? So, how about R? Heroin. Okay, let me say in the South. That's okay. So you can do your speciation chart like this with pH on the bottom. And then we put on there all of the pKa's. And so we have a 5.1 for quinine. We have a 9.7 for quinine. And then for heroin, we have a 7.5 or 7.9. Okay. And then we have all of these boxes, and we need to put in what species they are. Now, it says quinine's dibasic and heroin's a single base. So all the way over here on the right, there is the non-protonated version. So we start over here, we have Q and R. And then as we go left, we get more and more acidic. And so on the far left, everything's very acidic. So as we go towards the left, we get protonated. Okay, so then this is going to be QH plus and QH2 2 plus. And then this is going to be RH plus. So there's all my species. Did that make sense? Okay, fantastic. Now, it's saying in a liquid-liquid extraction with chloroform, what aqueous pH would separate quinine from heroin? So we want to separate these two. One needs to be aqueous, one needs to be organic. So we just need to find some pH in this chart where one is ionized and the other is not. So let me do this. This will be so fun. Blue. Okay, these are all in the aqueous layer because they're ionized. Isn't that visual? Okay, and so right here is a spot where one is in the aqueous phase and the other is not. So we would pick a pH of like 8.5 or something like that. And it says the answer is 9. So, and then the first, in problem 2, are just asking for the pH. Now I need to ask you, well, which one is in which phase? So it says heroin will be in the blank phase. So down here, if I pick this pH right here of 9, the quinine's mostly protonated and the heroin's not protonated. And so this heroin will be in the organic phase and quinine will be in the aqueous phase. So B, organic and aqueous. Does that help? All right, good. The speciation chart is the way to go because it's, now that 9 is pretty close to 9.7 and 7.95, and so you could get in there and figure out what percent ionized it is. Okay. What tends to happen in liquid-liquid extraction, let's say it's 85% ionized, and that 85% goes in the aqueous layer. Let's see, yeah. And then the unionized is in the organic layer, and the aqueous layer is gonna be kind of like a vacuum. It's gonna suck it in there. It's gonna rather be in the aqueous layer. So right where the aqueous and the organic layers meet, that's where the acid-base reaction is gonna go. And so pretty much all of the quinine is gonna go into the aqueous layer. It's gonna act like a pump because it's ionized in the aqueous layer. It's gonna be pumping into that layer. But there'll be more contamination of the quinine in the organic layer. So this, it kind of depends upon both their solubility and chloroform. And so there's some nuances that we're not going to have to test about. So never mind. Yeah. Any others? Yeah.
There's been a couple of multiple choice questions about which paper is the most dense or the least dense, but then we also calculate the densities for other gases as well. So for those multiple choice ones, are you just wanting us to know those off the top of our head? Or
yeah. So so if you just look at the I don't know what number that was in. Was that in 10 or?
There's one on 10 and then one, I believe on the last one that we had as well.
10 was kind of a long one just to kind of review for the test. There was just a lot of stuff. And so, let's see it on here. But, if you just look at the periodic table, I mean, you don't even have to do any calculations. The heavier the gas, the more dense. Like krypton is more dense than neon. Because the mole of a mole of volume, think about an ideal gas, it's the number of particles, regardless of their mass, that determines the volume. Okay, so a mole of any gas takes up the same volume. But if the particles in that gas weigh more, it's more dense because it's mass over volume. So the ideal gases all are the same in terms of the volumes that they take up, the pressures that they give. and in the density then is just the mass of that. So if you can calculate the volume of 1 mole, 22.4 liters, no matter what the gas is at STP. And so the heavier the gas is going to be more dense. Yeah. So you could go even like the organic molecules, hexane and octane and decane. Since decane is bigger, it's going to be more dense. It's easy to do in the gas phase. In the liquid phase, yeah, so I'm not going to ask you about liquid phase.
For number 10, number 16, I can't find as well Aspirin. Do you know what that is?
Okay, so yeah, that should have been in the notes. It's just a side thing. Let's find that though. Drug. No, that's drug. Here we go. Where is it? First pass. Okay, maybe it fell out of the notes. Like I've revised the notes, but yeah, here it is. First pass metabolism. That one little bullet right there. So you have absorption, ADME, absorption, distribution, metabolism, and elimination. And so, some drugs will be eliminated before they're metabolized or anything. So they just do absorption, distribution, and there's no metabolism necessary. If they're water soluble, a lot of times they'll just go right in, or no. If they're not water soluble or if they're really fat soluble, they'll stay in the gut a lot of times. And that's what happens with morphine. It has about a 50% F oral, and the F means first pass metabolism. So only 50% goes into the bloodstream if you eat it. So that's why they give it by injection. Same with a lot of other drugs that are just so fat soluble and they don't care about water. It's wasteful for you to eat them, because if you ingest them, they stay in your gut and they don't get into the body. They don't get distributed and they get eliminated. So you have to have absorption for there to be bioavailability. And so it's as if that drug was metabolized and eliminated before it ever got in. So they call it first pass. It just passes through the body. And that morphine is probably what I asked about in the homework. Was it morphine? Or did it just say a certain drug?
It just says the F oral is an drug.
Okay, so what are your options? Let's see. What number is that and what homework?
16 homework 10.
16 homework 10. So I'm on 33. Let me back up. Yeah, so it's again that percentage of drug available after oral ingestion. And so, it's confusing when you have one that's 50-50 because it's telling you how much was eliminated or how much was available. But the F oral is how much is available. So if you have like let's make it a worst case. Say you've got an antibiotic that's got an F oral of 25%. Then if you give it by pill, only 25% of that's going to go into the body. 75% is going to be eliminated through the gut. And so it's better to do that antibiotic by IV or injection so that it's put directly into the body's bloodstream so it can be distributed. Or to change the formulation in some way without ruining its effectiveness. So, yeah. Okay. What else? Okay, if you're going to wait until we're done and then ask me a question, you're going to really tick me off. So I always, that really does. That's one thing I can truly say upsets me. We have, like another 15, 20 minutes and to let everybody go and then get a private tutoring session when I know every question is going to help everybody else, Yeah, go ahead.
So, on homework 9, where you talk about like this stoichiometric ratio, like, would you give us that little like chart where it gives the percentage of what makes air?
Okay, like
Or is that like something you have to
the nitrogen, oxygen, that chart. Yeah. And I think I even let me just find the equation sheet for the exam so you guys can like go, right? Sound good? All right. So here's all the exams. Y'all are be like, click on that. Okay. So let's see. It's in here somewhere. Yeah, I'm memorizing my file tree so that you can hack into my computer. Sure. Yeah. Let's see. Thought I had. Oh, here it is. Exam equations. Ta-da. Okay. Hello. It's too big. Huh? I got like 10 PowerPoints open. So. Yeah. So that was the first one you guys see. No, this is it. This is it. Yeah. So here's the little dry air thing and all of that. This was the sensitivity chart for explosives, with TATP being ridiculous. I mean, I wrote a grant to study that molecule, and then I found out that it explodes wet. Like it's so sensitive that it just can blow up spontaneously, even though it's wet. And none of the other explosives blow up wet. So I read that from Lawrence Livermore. They put out an alert, and I was like, I'm not touching that stuff. For two reasons. One, I didn't want it to blow up on me, but really, I didn't want to have to fill out the paperwork. I was going to be worried about like really small amounts. It probably wouldn't have done anything to me and be in the hood, But oh my gosh, to have to write up the, So I did it all on Gaussian. So, okay, so this is now this is I don't recall any of the uncertainty analysis on this quiz. On this exam. So I don't know if this looks like it might have been for the final, right? That had everything on it. But yeah, you got what's missing here is the kinetics equations, and so it should have the kinetics equations on there. So this might. Let's see. That's the final exam one there. Let's see what I have for. Let me sort this way. Exam 2 equations. Here we go. 2021. Yeah, here's the first order kinetics. Here's like the stomach, pH, colon pH. Here's your Williams equation. And if you do some crazy quadratic formula for the ice table or something, which I'm not going to give you, but anyway. The delta H of combustion here for CHN and O. It's all right here, CHN and O. Here's the phi. Here's the molar mass of air just given for you. So you got the table and you got the result. Sensitivity scale for explosives. Yeah. Okay. Yeah. So this makes you feel better? Hopefully? Okay, good.
What kind of questions related to that sensitivity scale?
Like which of these explosives is the least sensitive?
Oh, okay.
And which of these? Yeah. That's right. Yeah. That's right. Which is the most sensitive? Yeah. Yeah, it doesn't say most sensitive, it just says very sensitive, and there's a scale. Yeah. And the explosives are down here in the, let's see, where do we have? I think I have them on the drugs flash page. Yeah. So here, I didn't think I saw it in the lecture, but TATP, this is triacetone triperoxide. So you see that molecule, look at it, 3 peroxides. The only molecule that has the 3 peroxides on our sheets. There's also hexamethylene, diamine, triperoxide. And this one is pernicious because you can make it straight from Walgreens pretty much, or AutoZone. You can buy acetone, you can buy hydrogen peroxide, and you can buy battery acid, sulfuric acid. And you very, very, very carefully mix those in a certain way, and you can get this explosive molecule. But it sort of you think, well, why are we not seeing these bombs everywhere, right? Because it blows up wet. I mean, there's no safe way to handle this stuff. So this is the idiot's explosive. They're going to make this and they're going to blow themselves to shreds. They're going to be, running around with, 2 fingers missing or something, because they had a small beaker of it and it blew up in their hands. They had some of this in a backpack in a subway. Well, I don't remember if it was Spain or not, but it blew up on the bomber guy before he could really inflict a lot on people. But we need to worry about that, because if they find a way to desensitize that molecule, then it's really pretty scary. So do you know what dynamite is? What the active ingredient in dynamite is? Like, what's the explosive? The original was nitroglycerin. But you say, but wait, nitroglycerin is super sensitive. It's not going to be safe to use. They mixed it with diatomaceous earth, and that made it not shock sensitive. And so then it was a safe explosive for traveling down bumpy roads on the back of a wagon with the horses and donkeys, taking it to the mine. And it's really how we mined gold and all of the precious metals back in the day, was using dynamite. And it was still a sensitive explosive, but they found a way to stabilize it. So that's my fear for triacetone triperoxide, is that they figure out a way to stabilize it so it's not dangerous. Yeah. Now this is nitrocellulose in the name, but this is a nitrate. I keep screwing that up this year. It has 3 oxygens. It's an organic nitrate, RONO. We have a minus there, a plus there. So this is an organic nitrate. And see, it's kind of like a nitrate ester. It's connected to that R group. And it's confusing if you see the name nitrocellulose, because that, and same here, this pentoerythritol tetranitrate. So that one at least tells you it's a nitrate. You see, it's the RONO. That's a nitrate group. These others are nitros. So nitroaromatics. Okay, see, there's only 2 O's, only 2 oxygens on nitro groups. There's 3 on nitrates, organic nitrates. So organic nitrates are pretty explosive. They're dangerous. And then these are what do you call these? Nitramines. So you have a nitro group stuck on an amine. So those are the things I want you to recognize. You were talking about the colors. Well, in terms of the explosive types, I'm looking for you to be able to recognize this is a nitroaromatic, this is a nitramine, this is an organic nitrate, or this is a triacetone triperoxide or some kind of triperoxide. Was there another one? There was so nitroglycerin, again, it says nitro, but it's really an organic nitrate. It's nitrated propane is what it is. Lead stiffnate, I don't know where the name stiffnate comes from. We could go to Wikipedia and probably figure it out, but it's a nitroaromatic. And then azide, this azide is a strange beast. It's got these 3 nitrogens, and that's not a stable group. All you got to do is give that guy a spark, and it turns into nitrogen gas, and it expands, and that's what your airbags are using. So you hit something, and the little pendulum in the front of the car swings and makes contact. The electrical signal goes to your airbag pack, it sparks those azides, and boom, you've got a big bag full of nitrogen gas. Now, it's so precisely timed. It's supposed to completely inflate and then start to deflate before you hit it, because you don't want it inflating while you're coming forward. Right? It's like leaning into a punch. It has to be fully inflated and deflating before you hit it, so it's soft. And so this hot gas has these little panels that pop out on the side, and the hot gas vents on the side. So a lot of times it'll burn your arms, but being a little scorched on your arms is better than going through the windshield. So, have you ever seen that? Have you seen burn marks from
Yeah, a little bit.
Really?
Mhm.
That's
They're not
interesting.
bad or anything.
Okay, I didn't know how bad they were. Yeah.
They're very like minor. It kind of looks like they just kind of rubbed it really hard on something.
Okay. Yeah, and that's why they like. I took had to take defensive driving. No comment. And so, so I noticed when I took in high school, it was 10 and 2, right? Driving up here, but the airbags throw your arms up and maybe into your face. If you're wearing glasses, that's not necessarily a great thing. And so the new thing that I learned in defensive driving was driving at what is it, 4 and 8, yeah, or 4 and 7, or 4 and 8, and so. Yeah, so you're driving like this, and then when you're turning, you're moving your hands like that, and then the airbags will just drop your hands down, and then you just hit it. But that's also why children were killed by airbags. And so they have a weight measurement in the seat. So when you have a child that weighs a smaller amount, then it doesn't turn on the airbag for the passenger. Okay. And I can see that too. Jennifer sits on her feet, so she like gets off the seat, and I see the little airbag thing on the rearview mirror turn off, and then she gets her feet under, sits back down, and it turns back on. So like when the weight goes off the seat, the passenger seat, the airbag turns off. That keeps the child from leaning forward and getting an airbag here and cracking the neck. Yeah, it's crazy how much technology goes into that stuff. And lead azide is the propellant that's used. Other questions? So we did pretty well. We've got it's 9:06. That's 9 minutes early. 9 valuable minutes. Any other questions? You got me the whole time. I'm not going to leave early.
Can you do 9 question 14?
Yeah, absolutely. 9:14. Okay, there it is. Oh man, that's going to be a long one. That's good though. We'll do it. Stoichiometric ratio of propene in air. Okay, is X percent. It's 6.4. We're done. No, but no, that's fine. We can do that. So, yeah. So we need to know that. Let's see. Let me go ahead and snip that one. That's going to be the combustion chapter, and here's the one page. Okay. So here's propane. We know the molar mass of propane because we can calculate it. Let me just walk through the methane one, and then we can do the same thing. But what we have here is we've got we have to calculate the number of moles of oxygen that we're going to need. And so that's the thing that's going to make it different than methane. Okay, so we write out the equation. Oh wait, what's going on here? That's what I want right there. Okay, so we write out the equation. The equation C3H8 plus O2 is CO2 plus water. Okay, so we're going to start with 3 carbon dioxides for the 3 carbons, and then we'll do the hydrogens come in pairs, so we have 4 waters, and so then we have to figure out how many oxygens we have. So over here, 3 times 2, we have 6 oxygens. Here we have 4, so we need 10 oxygens total. So, right, y'all catch me if I make a mistake. So then they come in pairs over here, so it's 5 O2s. So that's always nice when we end up with, it's not like 5 halves or something. If we ended up with 5 halves, then we would have to multiply everything by 2. But we're really trying to figure out for 1 mole of propane. So we'd probably just leave it as 5 halves because it's not going to really matter later. So now we need to know how many grams of air, because we're doing the stoichiometric ratio is a mass. So we want to know mass of propane per mass of air, right? That's what we're calculating up here. Mass of fuel over mass of oxygen. Okay. Okay. And so we've got this this molar mass of air. Okay, so we've got the 0.209. So we need 5 moles of oxygen. Okay. And it's 0.209 moles of O2 per mole of air. Okay. Does everybody follow that? Okay, now I need the molar mass of air. It was 28.9 grams of air. So this will give me the mass of air. It's 690.7. Okay. And then 1 mole of this, let's calculate the molar mass of the C3H8. So that's 36, which is the C3, plus another 8. 44. Okay. So we have 44 grams of C3H8 divided by 690.7 grams of air. What do we end up with? Do we get 6.4? Oh, no?
Yeah, I got to multiply by 100, so you'll get 0.06.
Oh, it's percent. Yeah. Okay. Yeah. 0.06, which then is 6.4%. Yeah. That's not too bad. So I just remember going like very slowly through this slide, and I was like, "Oh, this is going to take forever." But it's because we came up with this molar mass of air, which is going to be on the equation sheet. So it's not too bad. Yeah, excellent. And then that's the STE, right? Stoichiometric amount. If I say we have, whatever, instead of 690 grams of air, we have 2,000 grams of air, then that's the system. And you could do the mass, like, let's just do that. So instead of, so this is STE. And if we had cis, if we had 44 grams of C3H8 and 2,000 grams of air, then let's make it 4,400 grams of air. Okay, so that's 0.01. Is that right? Yeah, 0.01. So we have 1%. Cis, so phi is equal to cis over STE. Okay, so it's 1% over 6%. So what is 1/6? Okay. And so that was that thing for calculating the LEL, UEL. I mean, I don't get into this on the test, but I'm just saying that you've got the STE. What is your system, right? And so if you know your system, you could tell if you're in a danger zone. So that 1% over 6% was pretty safe. We were at 0.16. If we were at 0.25 or more, it might be flammable. If we're up here close to 1, like 0.8 or something, then it's an explosive environment. We're so close to the propane air perfect mixture, the stoichiometric mixture, that it could blow up. Okay, excellent. Thanks for asking your question. It's 9:14, 9:15. We did it. Yeah.